All right. It's a real pleasure to introduce Zigeng Chen today. Zigeng has been part of the Agroecology lab since 2024 in January. So it's been a little bit more than 2 years. It's been working hard on collecting data from some of our collaborators at other LTAR sites. And so he's coming from South Dakota State, where he did his PhD, also related to rangeland. So he was doing a PhD on rainfall manipulation of all things. And he was looking at how rainfall manipulation influenced soil fluxes and nitrogen cycling. Originally, Zigeng comes from Shanghai, China. So he came from a long way. And in his spare time, he's a very avid Warhammer player, I heard. So if you like to play Warhammer, you can ask him about that. And so today he's going to talk about pretty interesting data coming from the LTAR network on net carbon balance across grazing lands. So here you go.
Okay, good afternoon, everyone. So today, my topic is about the agriculture's productivity and carbon balance across U.S. grazing land. Before I start, I will ask a question for anyone who has stayed here in the last 2 years. Do you remember how many seminars we're talking? The topic is about the carbon balance, it's about the productivity. I can tell you, among almost like 60 to 70 seminars, there was less than 3 topics about that. So you see, people wasn't really care about the carbon balance. like a station, biological station, like an Archbold, we focus on things we can see, like vegetation, birds, animal. But for things we cannot see, like carbon dioxide, like methane, people just doesn't see the importance, doesn't see the situation in the United States. So hopefully today I will give you like a big picture, not too deep, just a wide picture about what is the carbon balance situation in the United States. So let's start it. What is the carbon balance? So the autotrophic respiration comes plants, and the heterotrophic respiration from the animals together becomes the ecosystem respiration. And all the carbon fixation and carbon uptake goes through the photosynthesis globally. Together, we have the gross prime productivity, we also call it GPP. Together, we use the GPP minus ER. The difference is called net prime productivity, NEP. If this value is a positive value, which means GPP is greater than ER, which means we have more carbon uptake than carbon release into the atmosphere, we said the balance is a carbon sink. And on the other hand, if we have more carbon releasing the atmosphere than what we uptake, we call it a carbon source. So why we care about the carbon balance on the grazing land? So globally, the grazing land store approximately 20% of soil organic carbon and release 14% of greenhouse gas annually. And in the United States, the grazing land occupies 27% of terrestrial land area and support 87 million of the cattle. The grazing land across the United States, you can see almost all concentrated as the middle western area and the southern east area. The distribution of the grassland, savanna, and shrubland highly correlates with the distribution of the cattle in the United States. So understanding the carbon balance on the grazing land will help us to better understand, to better assist them to help us cure the beef production and the soil health in in the land in the United States. That was the first question. So what is the carbon balance across the grazing land? Before we started, we have to introduce a new concept, a new indicator called net ecosystem carbon balance. I have already introduced you the NEP, but the net ecosystem carbon balance does not only have the carbon dioxide, it has to contain everything, the methane from the enteric fermentation and the manure, the harvesting and the soil elements from the carbon directly, the grazing, the leaching, the fire emission, the soil erosion, everything together. We sum all the input and output together, then we calculate the NECB. But you see, some of the flux like leaching, fire, soil erosion, they are pretty irregular and really hard to estimate or measure. And the harvesting, soil amendment, and grazing, they were seriously controlled by the landowners and the managers. So it's also hard to estimate. So can we find the study sites across the US which we can control all those inputs and outputs, and only keep the carbon dioxide and methane, these two of the most important, the first and the second largest carbon flux in the ecosystem, so that to simplify our estimation and the calculation. Here, I will introduce the long-term agricultural ecosystem research network, also called ELTA. We have 18 ELTA sites across the whole. Among them, 8 of them are the grazing land, or we said the integrated system has both the cropping and the grazing land. You can see most of them, they're located in the western area, and we, Archbold, are here, the lonely island located at the southeast. Among all the 8 sites, Archbold is the only one, and we have the 4 pasture, or we say study sites, 2 of them in the Buck Island Ranch and 2 of them in the owner. For the rest of the sites, like the Great Basin in the Idaho and the Wonder Gorge in the Arizona, they each have 3 pastures. Safer in the Colorado, also Southern Plain in the Oklahoma, they both have 2 pastures. The rest all have 1 pastures. And another advantage of the ELTA sites is within each of sites, we have at least 1 eddy covariance tower. This is the major instrument we use to collect the carbon dioxide data. So you may want to ask me, what is eddy covariance? So eddy means a turbulent wave of air which carry the gases and moves vertically from the atmosphere and the surface. And covariance is a statistical method used to measure the simultaneous relationship between the wind speed vertically and the gas concentration between them. The eddy covariance tower will measure these 2 variables in a high frequency, and when I say high frequency, that means 10 to 20 hertz, which means 10 to 20 times per second. And the eddy covariance towers also connected to the other sensors besides the carbon dioxide sensors. So we also connect to measure the precipitation, the air temperature, solar radiation, soil water content. And for those sites, some of the data was also missing in like a specific year. In that way, to fill the carbon dioxide data, in the select year, which I mean, in at least continuous 3 years, we will download the AEP data directly from American flocks, which was also a network globally that the personal investigator in their electrosurveillance towers, they will upload their data to this website, so researchers can download freely. Yes, so to calculate the NECB, that equals GPP minus ER, which is NEP, minus all the methane flocks, the sum of the methane flocks times 0.75. This is like a conversion parameter to transfer the carbon in the methane to the carbon in the carbon dioxide. And methane EF means the methane emission from anaerobic fermentation and also the methane from manure. Methane flux from anaerobic fermentation equals SR times alpha. SR means stocking rate, which is amount of the cattle per area in a specific time. Alpha is the methane production rate per day per cattle. This was cited from multiple reference in the previous study. Methane flux from manure equals methane from anaerobic fermentation over beta, and beta was another parameter was cited from 20-year study in the beef, the greenhouse gas emission in the United States. Oh, and besides the biophysical variables and the flux variables, we also want to bring in the management variables. And among all the managements, most important is the stocking rate, is the number of the cattle. But you see, the stocking rate is not a standardized unit. You can imagine if we have 100 cattle, be different from another 100 cattle in the Arizona or New Mexico. That's because the ecosystem capacity, the background biomass in the different ecosystems are completely different. That way, we will introduce the grazing pressure index, which equals the stocking rate over the peak standing biomass in each ecosystem. So peak standing biomass is the highest amount of the biomass annually. Okay, now we have all the data, all the information we needed. So what kind of information we can extract from it? So first, the mean annually precipitation and the mean annually temperature across all the sites in multiple years. You will see we are here. This is the Archbold. We have the highest mean annual precipitation and the highest mean annual temperature. And look at here. We almost have a linear correlation between the temperature and precipitation. That, yes, definitely makes sense. But we are also seeing some sites. Here is Wanagotch in the Arizona and the Jornada in the New Mexico. They have great temperature, but the low water variability. And please remember this, it will help in the next few slides. Then next, let's have the let's compare the AECB with the MAP, MAT, and the GPI. So first one, each red dot means the mean annual precipitation, and the green bar is net ecosystem carbon balance. And if it's a positive value, which means we have more carbon uptake than release, so it's carbon sink. And if it's a negative value, it means a carbon source, means more carbon released into the atmosphere. So you see here, we almost have the linear regression that with a greater mean annual precipitation, we have a greater NECB. And for the mean annual temperature, almost the same trait, that the higher the temperature, the higher the carbon sink. But for the grazing pressure, okay, doesn't really follow the same trait because the two sides with the first and second largest grazing pressure, we have a negative value, which means we have a carbon source. And let's put all the three plots together. You can easily see for most sides, they are all positive value. They are all positive value, except NP means Northern Plain in the North Dakota with the driest and the coldest sides. Or another negative side is the Nebraska. They are in the middle temperature, middle precipitation, but has the highest grazing pressure. So this is the first result we can have, that the NECB are carbon sink across all the grazing land, unless it's covered with the low temperature, low water, and heavy grazing. Then this is just a simple comparison between one variables and carbon flux variable. Now we want to know the interactive effect from temperature, precipitation, and the grazing pressure. Here we will bring the Jason Newman method. You don't need to know what exactly is this method. You just need to know this examine the interaction of two variables. So first plot, you see the blue area means the significant effect of the MAP. The red area means insignificant effect. The y-axis says the slope of NECB over MAT, which means the effect of MAT on the NECB. The green dash, vertical dash line is a threshold, which means when MAP is greater than, here is almost 715 millimeter, the effect of MAT on NECB is a positive value, which means when the precipitation is not limited, when water is not limited, the temperature has a positive effect on the NECB, which means the greater the temperature, annual temperature, the greater the carbon sink we have. And the interaction between the temperature and the grazing pressure, you see here, if the precipitation, annual precipitation is less than 1,000 millimeter, that the grazing pressure would have a negative effect on the NECB, which means when water is limited, the grazing pressure will reduce the carbon sink, will promote the carbon source. And the third one, if we will look at here, similar to the precipitation, when temperature is limited, the grazing pressure would also promote the carbon source, will promote the carbon release into the atmosphere. You also realize here that when temperature is not limited, when it's warm, hot sites, the grazing pressure, which means the more grazing we have, the greater carbon sink we have. That doesn't really sound right, because you cannot imagine in a place like a desert we have enough heat, then the overgrazing will promote the carbon sink. That doesn't sound right. So we'll go back to this plot, which means because the high correlation between the temperature and the precipitation, so those kind of positive effects does not bring by the heat, but bring by the precipitation. Then next, if we build a simple linear regression between the NECB and the mean annual temperature. Then we treated every the correlation among each of the sites. Then we treated the slope. We treated the slope of the line between the AECB and MAP as the sensitive of the carbon balance to the precipitation. Then we also treated the interannually variation of MAP as the value called the coefficient variance of MAP. And we build another linear regression. We will find the sensitivity of the carbon balance to precipitation has the significant negative effect with the coefficient of the annual precipitation, which means for those arid and semi-arid sites, for those sites, you have the huge interannually variation on the precipitation. They have very low sensitivity. They have very low sensitivity to the AECB. The carbon balance has a low sensitivity to the mania precipitation. But on the other hand, for those tropical, subtropical land, for example, Florida, for those sites, they have a low interannually precipitation variation. They are very sensitive to the change of the annual precipitation. So which means the carbon balance in the water non-limited area, they are sensitive to the annual change of the precipitation. Oh, yes. So then that we put all the pictures together. That will give the two conclusions. First, all the grazing land across the United States is carbon sink, unless it's restricted by some of the low water, low temperature, and heavy grazing. And the second, AECB is sensitive to the precipitation under the interannually variability. Right now, we focus on the AECB, net ecosystem carbon balance, but we know the AEP actually has highly correlated with the AECB. Actually, the carbon dioxide emission occupy the most of the carbon flux. Methane from actually fermentation and manure only occupy 0.4% to 4% among all the sites. So the next step we want to do is dig a little deeper, focus on the AECB. We want to know what kind of phenology matrix and biophysical factors will control the NEP, the net ecosystem productivity. So let's bring a new concept called the phenology matrix. So the start date of the growing season, SOS, end date of growing season, EOS, and the growing season length, GSL. How we determine these three phenology matrix annually? We will use the 50% of maximum daily GPP, which is the data was directly extracted from the elecovariance tower, the daily GPP value. So now imagine for each site, we have daily GPP data. We know what is the maximum daily GPP here. Then we determine the 50% of maximum daily GPP. Then the first date when the daily GPP reach 50% of daily maximum, we call it SOS. And the last day annually, they still keep the 50%, we call it EOS, end of season. And the date between SOS and EOS is the growing season length. And this is the average length of a growing season in all the 8 sites. And the green line, which is the upper and the low, the high and the low limited for the start of the growing season and end of growing season. And this is you see our Archbold we have the longest growing season, earliest start of growing season, and the latest end of growing season. And for sites like in the Nebraska or the Oklahoma, they also have the second and the largest longer growing season here. So the linear regression between the phenology matrix on the NEP, ER, and the GPP. You see, the end of the growing season and the growing season length has the positive significant effect on the ecosystem respiration and the growth prime production compared to the start of season. And also for the NEP, though the model was not that fit, but still growing season has the largest the fit than the start and the end of growing season. So here remind us the growing season length. The end of growing season make a better prediction compared to the starting growing season. And the growing season length is one of the best phenology matrix to correlate with the 3 carbon flux variables. So now we have the phenology matrix. We want to then the phenology matrix and the biophysical variables, the effects on the AEP. And now we want to bring a new model called generalized adaptive model, aka GAM. You don't need to know what exactly is GAM. You just need to know this is the exam, the nonlinear regression between the response variable and the productive variable. We will bring here, we will convert the growing season length to the number of months. That's another way to represent growing season length. And we also have the monthly precipitation, monthly global radiation. This one to replace the temperature because the radiation has a high correlation with the temperature. Then the soil water content and the enhanced vegetation index. This is the data also extracted from the Landsat remote sensing data. So here, we will see the nonlinear relationship between the number of months for each set each year has this kind of curve with the NEP. Here you see between the 2.5 and 7.5 months, the growing season length, they actually have the negative effect on the NEP, although it's a significant effect. And for the precipitation, this is the mostly precipitation. Unfortunately and unexpectedly, they did not have a significant effect on the NEP, on the monthly NEP. And if you look at here, the tail of this regression line, you will see they have a really wide variation because when monthly precipitation above 400 millimeter per year, there was almost no data. The only data points come here. That is what we recorded in the ONA Florida in 2022, September, which was brought, we have 700 millimeter precipitation in 1 month carried by Hurricane Ian in 2022. The third, the solar radiation. So when the solar radiation is between 500 million joule and 1,000 million joule in a month, the radiation has a positive effect on the NEP, and this is almost like an optimal windows for the NEP. And for the soil water contents, this is almost similar a similar trait that between, I think it's 30% to 45% of volumetric soil water content is almost like another optimal window for the net ecosystem productivity. And also for the EVI, when the enhanced vegetation index is greater than 0.3, it almost have a positive, almost a linear significant effect on the EVI, which suggests that the vegetation condition when they, let's say, reach a level, they will like significant promote the the productivity. And we also find among all the five variables, radiation and the enhanced vegetation index contributes the most to the nonlinear regression model. So they are the most important inferential variables to influence the productivity. And after we know the contribution from all the variables, now we will use the random forest model to predict the AEP and use them to compare to the eddy-correct tower measure the AEP. And again, you don't need to know what is the random forest model. You just know it's the machine learning mechanic used to estimate the data based on the nonlinear regression between the multiple biophysical variables and the AEP. So you see the model fits pretty well, and the mean square error was only 0.09 microgram carbon per meter square. So it's pretty good. So what conclusion can we have? First, phenology controls the seasonal process and help to explain the AEP. And second, the relationship between the biophysical and the AEP are nonlinear. And third, the solar radiation and the vegetation index are the most important predictors on the productivity and the carbon balance. And now let's put the first question and the second question together. This is the take-home message. First question, we ask, what is carbon balance across the United States? Now you can tell other people that carbon balance across the United States are carbon sink, unless they are constructed by the environmental stressor. And second, phenology and the other biophysical variables have a nonlinear influence on the carbon balance and the productivity. So what is next things we can do to promote, to improve our study? We can, this is another thing because of the way why I use the we estimate the methane emission is because Florida and Nebraska are the only two sites has the methane sensors on their eddy-correct towers. None of their other sites have any methane sensors. So maybe the other sites, we can just get more funding and buy more equipment. And the second way, long-term monitor. The benefit from the LTIs, we have the long-term monitor of those variables. But right now, we only have 3 to 4 years continuous variable for all sites. In the next level, maybe we should have 5 years, 10 years, even maybe 20 years monitor. Then maybe we have more clearly picture of the carbon balance situation in the United States. And the third, we know the AI was a new cake in the future. So maybe we will bring more remote sensing data to the study and the management practice. Currently, we only have the stocking rate, grazing pressure, And in the future, we wish we can brought more the human influence to the study. I want to thank Nancy, Maria, Roosevelt, and Shafali's work in this study. I have another 21 co-authors to help me finish this study, and all the non-authors across all the sites, USDA, institution, Cornell University, all the other institutions. I will thank you for all your help. This is all the reference, important reference for the study. And now we all, and I will open to all your questions. Thank you. Yes, please.
Great talk again. So when you were showing us the NECB with the MAT, MAP, GPI, and you had Archbold had those 4 sites, like those gray bars, it looked like one of the sites from Archbold had like twice the NECB than the other 3 sites. And I was just wondering if there was any clue why. I think one of them was an ONA, maybe.
Okay, hold on.
Yeah.
Are you talking about here?
Yeah, so like AOP, that site looks like it's, twice as much.
Yes.
NECB, so what's the
So AOP is the site in owner, also dominated by the flatwoods. So it's a pretty well maintained pasture. So
it's flatwoods though? Like, do you mean that there's more, is it different than like our improved pastures at Island?
Okay, so the AOP sites, oh wait, hold on a second. Let me no, I was wrong. AOP is actually the site has the highest grazing pressure among all the sites. Because, well, this probably could be another point so we can dig in. That's the heavy grazing seems to promote the carbon balance in the sites if the sites has sufficient water and temperature, because the biomass protected in those kind of sites are pretty well. The renewal of the above ground vegetation was quickly, so they have the huge carbon sink in the high grazing sites. Yes. Hurry, please.
I think it might be worth looking at that owner site. I think they also apply more fertilizer, so it would be good to check the.
Yes, but unfortunately, this data was collected in 2021 to 23. During that period, at least Maria told me, she didn't have any fertilizer on that time period.
Yeah, and the flip side of that is I think they have applied fertilizer there in the past. So
oh yeah. It may have some kind of remaining in the soil to promote.
That really wasn't my question. Sorry about that.
Excuse me, I understand Maria's saying yes, proper grazing management, nutrient addition, annual nitrogen application.
Good, we'll leave it around that. So thank you, Maria. The question I was most interested in was the methane emissions, particularly the wetland methane emissions, which are not part of this because you don't have methane sensors across all the towers.
No.
But in reality, the places where you would expect the largest methane emissions are Florida, just from if you look at methane emissions. So what if you actually ran the southeastern ones and just added the methane in, because we do have the sensors, assuming that it's a much, much lower impact on those dry western sites? It's just a thought.
Yes, exactly, because we are the only sites, we have the floating and like a float cover. The land was covered by float for like a couple weeks, even months, compared to all the other sites. Then yes, it makes sense to monitor to use the methane sensor data here in Florida. But to keep the consistency with all the other sites, I have to give up this idea. But if we want to dig in the methane emission in the Florida, we can have like a separate.
I think it would greatly reduce our sink values by putting that in.
They have a huge emission. Oh, sorry, emission, yes.
Just a thought. I mean, I can understand the consistency across multiple sites, but I do think it's a very important caveat for the Archbold site.
So it's really cool to know that grazing lands are a carbon sink, but are they, at least these research sites, are they actually stocked at the level that they could be? Like, is there a way for you to come up with thresholds for when they can be carbon neutral versus carbon sinks versus?
Yes, please. Yeah, that's a really, really good question. So one of the things we find is all the PIs, the personal investigator, or the land managers among elder sites, they won't overgraze on their study sites. So the stocking rate was always below the carrying capacity of the land. So in that kind of level, like yes, all the I would just say the grazing pressure in sort of a level will promote the carbon sink, will promote the vegetation growth. So yes, if we compare the elder sites data to the other just normal landholders, the stakeholders, then we may have a very different result because other people may just the economic demand might be of priority compared to our scientific study. So yes, you're completely right. Yes.
You said that you used the random forest model, right? And like, how many data points did you use to train the model?
492 for the monthly simulation. 15,559 for the day. I don't remember, but yes, 200.
That's
Did
great.
you split the data set?
What?
How did you split the data set into the training and testing?
For that part, I was yes, I was follow the instruction from the from some paper. They didn't tell me too much about the training. Yes.
I see on one of your slides on the sensitivity that the Archbold sites are really sensitive. And is that, yeah. So does that mean that they, like maybe you could just explain this one again. Like, is it sensitivity is in the sense that like ability to be a carbon sink?
So you see, I use the slope between NECB over MAP as the value of sensitivity. So which means how much the precipitation change, the amount of precipitation change, how much the NECB change.
Just to the precipitation, not to the ability of it to be a carbon sink. Just the product, or just the
just the mean annual precipitation. Then we compare the sensitivity over the coefficient of MAP.
So does that mean that those sites are more sensitive? So if there's a change in precipitation, then the ability for Archbold sites to be sink changes. Is that what that means?
Yes, you see here, actually Florida, the two sites in the Archbold are different from the two sites in the owner. So for us, for the Buck Island range, that yes, if you have like a very few interannually change, like a little reduce, a drop, increase or decrease of annual precipitation, then yes, they are really sensitive to the change. Yes.
To continue on this slide, how do you explain that the two sites, the four sites from Florida are varying so much in terms of the coefficient of variation in MEP?
Another good question. which I am not quite sure, but I would expect because the two pastures located in the Backland Ranch was actually take a large area, and these two pastures in the owner, the area was pretty small, like I think 20 acres in the owner, and maybe we have like 10 times bigger in the Backland Ranch. So the scale of that area might be cause the difference.
I wonder, Zigeng, also that we are pumping during drought condition in Buck Island. And they are not pumping, they don't have any pumping in from a big canal system in Ona. So I really wonder if that might ameliorate or sort of slightly change that relationship. They're on a lower elevation, less extreme drought on those higher drought pastures. Greg might disagree with me, but it's hard to cope with the pumping in addition to the precip because it definitely ameliorates drought condition. You didn't want to hear that, but
Maria seems to agree because management has a large impact on carbon balance.
One thing I wanted to say to you is again, I thought the way you're looking at all of the weather data, the full suite of it is very interesting for all the other programs here. We're sort of stuck with, what is the precip or last winter's precip. And I really like the elegant way that you looked at lots of other measures of, annual variability in weather or climate. And I would encourage everybody to think about that, even if they're not that interested in carbon. There's a lot of ways of looking at weather patterns and drivers here. So thank you for that.
Any other question?
Okay, we good? If we don't have any other questions. Thank you, Zigeng.